Okay, so one of the things that is going to be on the final exam is evaluating functions at certain values. So let's say you are given a function g of t equals 7t minus 4, and it says to evaluate the function at 25. So it says to basically find g of 25. So when we're evaluating, the number that is in parentheses, that is equal to t, because it's in the same location. So that tells us that t is equal to 25. So that means I can replace t with 25 on the right side. So g of 25 is equal to 7 times 25 minus 4. Now when we're evaluating, we're just doing the order of operations on the right side. And when we have function notation, we don't do anything on the left. We're not solving for g. We're evaluating, so just doing the order of operations. So I need to do 7 times 25 first. So that's 175 minus 4. And that gives you 171. So we would say that g of 25 is equal to 171. So that's an example of evaluating a function. Let's see, what else do we have that's related to functions? There is function composition and function inverses, function addition, subtraction, multiplication, division. The composition is the hardest. So let's do a function composition. Let's use the same function, g of t, and then let's say we have f of t equal to, let's see, on the homework we had a square root. Let's do an absolute value of t plus 7. So let's say you were asked to find f of g. F composed g, it has that circle. And you're given, we have our g of t, which is 7t minus 4, and our f of t, which is the absolute value of t plus 7. So this is a function composition. This means that you're plugging g of t into f of t. So everywhere that I see t, I'm replacing it with g of t. So my function f is absolute value of t plus 7. So instead of t, I have g of t, then plus 7. Then I need to go and replace g of t with what it's equal to. So g of t is equal to 7t minus 4. So I need to plug that in for g of t. So my absolute value, then I have 7t minus 4, and then I have my plus 7, and I'm closing the absolute value. And then you're simplifying inside. So I can do -7 plus, or -4 plus 7, which gives me 3. So this will give us the absolute value of 7t plus 3. And we can't simplify that anymore because you can only take the absolute value of things that have numbers. So because we have a variable in there, we can't actually take the absolute value at all. We can't split that up. So that would be the function composition. Now the other thing on the final is you could be asked to find inverses. You can only find inverses of things that pass the horizontal line test. So f of t, the absolute value graph gives us a v. This does not pass the horizontal line test. We can't find the inverse because I draw a horizontal line, I hit the graph twice. So there's no inverse for an absolute value, but there is an inverse for a linear equation. So I have this g of t. We could find the inverse of g. Oops. So if we want to find g inverse of t, first you replace g of t with y. So we have y equals 7t minus 4. Usually when we do inverses, we have x and y, but t is fine as long as you're consistent. Then when we find the inverse, we flip them. So now it's t equals 7y minus 4. And then you solve for y. So I'm going to add 4 to both sides. So I get t plus 4 equals 7y. And then I'm going to divide everything by 7. And I like to have my y on the left. So that would be t plus 4 over 7. So once you've solved for y, that's your inverse. So g inverse of t is equal to t plus 4, the whole thing, over 7. So those are like the 3 things that you're going to be asked to do with functions, is basically evaluating a function, doing a function composition. You could also be adding, subtracting, multiplying, and dividing functions together, and then function inverses. So do you have any questions on any of those 3?
No, I think those look pretty good. I think I might got a grasp on those.
Okay. The next sort of things you're going to be asked about are like function transformations, domain and range, those sort of things. So domain and range, we usually ask them in terms of rational functions because those are the ones that have the most interesting domain and range. I think actually you're only going to be needing the domain on the final. So I don't have any rational functions here. So let's say we have h of x equals 2x squared over x plus 5. So, and you're asked to find the domain. And we're going to have some questions on rational functions, so we can do a few other things with this too. So the domain of a rational function is where the denominator is not equal to 0. So our denominator is x plus 5, so that is not equal to 0. So I can just solve that for x, get that x cannot equal negative 5. And so we can write this in set builder notation where you say, oops, well, x cannot equal negative 5, and we're just assuming x is real numbers. Or if you want interval notation, you're going from negative infinity to negative 5, and it's an open parenthesis at negative 5 because negative 5 is not included. And then we have the other end, negative 5 to infinity. So that would be the other way of writing the domain if you're not including one specific value. The other thing that we do with rational functions are finding the vertical and horizontal asymptotes. So the vertical asymptote is where your asymptote or your denominator is 0. So it's basically the same thing as what's excluded from the domain. So you just set your denominator equal to 0, and then when you solve, we get x equals negative 5 as the vertical asymptote. Then when we have those horizontal asymptote, we're looking at the degree of the top and the bottom. So on this particular example, the degree of the top is quadratic, so that's degree 2, and the bottom is linear, so that is degree 1. So the top is larger than the bottom. When that happens, we have a slant asymptote, and we need to do long division. because we have a linear in the denominator, we could also use synthetic division. But I'll do the long division just for good practice. So I'm taking what's on the top, and then I'm dividing it by the bottom. And when I'm doing long division, we always look at the first terms here. And so I want to divide x into 2x squared, or ask myself x times what can get me to 2x squared. So I can multiply my x by 2 and another x. So x times 2x gets me 2x squared. Then I take that 2x and I multiply it by the 2x plus 5 and write it underneath. So that's 2x squared, and then 5 times 2x is 10x. So I'm going to have to put a placeholder here. That's a 0x up there. And then we're subtracting these. So I'm going to draw the line, and then I'm going to change all the signs because we're subtracting. So then we have 2x squared minus 2x squared, which is 0. 0 minus 10, so that's negative 10x. And then again, I'm going to look at this negative 10x, and x times what can get me to negative 10x, and that's negative 10. So then I multiply my negative 10 by the x plus 5. So I have x times negative 10, so that's negative 10x. And then 5 times negative 10, which is negative 50. And then I have to put another placeholder. And then when we subtract, that ends up changing all the signs, and I always circle them so that I remember that I've changed those. So all of those negatives become positive. So then I have 10x plus 10x, which is 0, and then I have 50. And 50 is a remainder because you can't multiply by x by something to get to 50. Now, when we're finding slant asymptotes, we don't care about the remainder, we just care about the first part, what we're dividing by. So this is our slant asymptote, 2x minus 10. So, oops, don't mean to have the highlighter, or there we go. Oops, I erased too much. So our slant asymptote is y equals 2x minus 10. So that's what happens when the top is greater than the bottom and you're trying to find a horizontal asymptote. You actually get a slanted asymptote where you need to do long division. Are there any questions on the rational function here?
I'm good on that.
Okay, Joseph, I know you came in as I was going through that slant asymptote. Do you have any specific questions on anything? If not, we're basically just kind of going through all the different things that you're going to see on the final exam. So we've gone through evaluating functions, finding function compositions, finding inverses, and then we just did stuff with rational functions. The next thing that I was going to pick was going to be polynomials, because those are another big thing. So let's see, let's do a polynomial. And let's see, this is difficult because if I just make up a polynomial, it's going to be really gross if I just pick up from random numbers. So I'm going to work backwards to make something up that factors nicely. So hold on a bit while I do that. Okay. So let's say you have a polynomial. I'm just switching letters here. So I did H. We'll just go through the alphabet. We'll skip I. We'll do J. J of x. Let's say your polynomial is x cubed plus x squared minus 8x minus 12. And you are asked to find the zeros of this polynomial. So to find the zeros, you need a factor. When we have a cubic, the only way to really factor this is to kind of do guessing and checking with synthetic division. And so you'd want to use the rational zero theorem to eliminate your possibilities, to at least give you some starting point. And the rational zero theorem comes from the first coefficient and the last coefficient. So the first coefficient, we're going to use 1. The last one, we're going to use negative 12. And this is P. And, nope, I got those backwards. Q is always first. Q and then P. And then rational zeros come from factors of P and Q. Now, because Q is 1 in this case, we're just looking at all possible numbers that divide into 12. All the factors of 12. And you can get positive or negative versions. So that's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, 6, and 12. So to factor this, I want to pick from some of those numbers, and I'm going to do synthetic division. So I need to set up my coefficients. So I have 1 for the x cubed, 1 for the x squared, negative 8 for the x, and then negative 12. And then I need to just start picking numbers. So I like to start with 1 because it's easy. And so we just multiply and add. So 1 times 1, multiplying those two together, that's 1. And I can put it on top. 1 plus 1 is 2. 1 times 2 is 2. 2 minus 8 gives me negative 6. And then I can see that I'm not going to get to 0. That's my goal. 1 times negative 6 is negative 6. This gives me negative 18. So if I was to think about this on a graph, I have 1 and negative 8. So I have an ordered pair here. That's what I found. Synthetic division can give you an ordered pair. And I need something close to 0 for the x, or for the output here. So I might want to pick like negative 1 or something larger than 1, like 2, and hope that it goes in either end. So let's say I want to try negative 1 because that's not that much different. It's pretty easy. So I'm going to just try negative 1 instead. So negative 1 times 1 is negative 1, and negative 1 plus 1 is 0. Negative 1 times 0 is 0. 0 minus 8 is negative 8. Negative 1 times negative 8 is 8. 8 minus 12 is negative 4. So I didn't get 0. I still haven't found a 0. But now I know at negative 1, I'm at negative 4. So let's say that's like somewhere here. So I'm getting closer to having 0 on the y. So you can kind of use this to help visualize. So right now, if I'm kind of graphing this, it looks like my graph is at least going this way. So maybe if I try negative 2, I'm going to find a 0 here, because if I look at where my numbers are heading, it's got to go up, or I'd hope so. So let's try negative 2. And this is the thought process when you're guessing and checking with synthetic division to try to factor something or find the zeros. So negative 2. So I have negative 2 times 1, so that's negative 2. Negative 2 plus 1 is negative 1. Negative 2 times negative 1 is 2. 2 minus 8 is negative 6. And now I can see this is going to work out nicely. Negative 2 times negative 6 is a positive 12. 12 minus 12 is 0. So I have found that at negative 2, I'm at 0. So I found one of my zeros. So if you're asked to find the zeros, I found one. X equals negative 2 is a 0. If you're asked to factor, I've also found a factor. That 0, that means that x plus 2 is a factor. It's the opposite sign there. So let's say you're asked to factor this. I now know that I have x plus 2 is one of my factors. And then I take this, and that gives me the second half of my polynomial here. So we started with something x cubed. So now this is going to be an x squared because I already removed an x. So that gives me x squared minus x minus 6. And once I get to something that's quadratic, I factor or use the quadratic formula. So I picked this because this is factorable. So this factors to x minus 3, x plus 2. So I've got two numbers that multiply to negative 6 and add to negative 1. So that's negative 3 times 2, which gives me negative 6. Negative 3 plus 2 is negative 1. So now I factored this polynomial, and then I can get my zeros. I already know 1, 0 is x equals negative 2. My 0 comes from x minus 3. It's generally the opposite of the sign, so that gives me x equals 3 is a 0. And then I have, again, x equals negative 2. So that is a repeated 0. So a repeated 0 means that it's going to bounce at negative 2. So all the graphs have to do, you can do with Desmos, but if it's going to bounce, that means that it's not going to cross, it's going to bounce. And so our graph is going to go look something like this. And then I know at 3 it's going to hit 0. So it's going to look something like that when you graph it. This is a really messy sketch. But that matches the end behavior. So our polynomial had a positive coefficient in the beginning, and it's a cubic. So the general shape of the cubic, the end behavior looks like this when it's a positive coefficient. So that matches based off of the numbers we got. What happens in the middle is kind of in the middle. So if you're asked to find the zeros, and if it's not factored, you're going to have to use like the rational zero theorem so you can guess and check. And then you need to go through and factor it. And then once you get to a quadratic, you can factor, use the quadratic formula, and then you set each of those equal to 0 to basically find those zeros. Related to polynomials is you can work backwards. Like if you're wondering, well, how did I determine that was a good polynomial? Because I said that I needed to work backwards in order to come up with one that was going to come up with nice numbers. So you can work backwards if you're given the zeros. So let's say you're given two zeros, negative 3 and 5. You're going to work backwards by putting one side equal to 0. So I can add 3 to both sides. That gives me x plus 3 equals 0. And then I could subtract 5, and I get x minus 5 equals 0. We're reversing the process, so we're creating a polynomial with these zeros. So you set those multiplied by each other. Let's say I'm going to call this k of x. And then you multiply that out. So this would give us x squared minus 2x minus 15. So if you're asked to create a polynomial based off of the zeros, you're doing the opposite of what we did when we factored. You start with the zeros and you undo everything to get it back in a factored form, and then you multiply. You guys have any questions?
No, but that was pretty amazing to see it the other way.
To see it going backwards?
Yeah, just like my mind is blown right now.
Yeah, it's just you're literally reversing everything you did, and that's how I can come up with polynomials that I know are going to work out. Because otherwise, if I just make up a polynomial, most of the time they're going to be really gross. So I have to work backwards.
Right.
And that's a skill. Let's say I'm trying to think of, maybe you are trying to design something and you know it has to be at 0 at certain points. You can use that idea to work backwards to create like what you're trying to model, what your model needs to look like. That's probably more of an engineering use than probably anything else, but that is something that you can do with this kind of technique. And I did kind of gloss over this, but I was showing how the synthetic division also gives you function values. So one of the things that you could be asked is like to use synthetic division to find a function value. Like say it says to find j of 2. So then you would use 2 for your synthetic division, and whatever your output is, that's your ordered pair. So I demonstrated that when I was doing the synthetic division, and it's a good way to kind of help you graph it as well. So let's see, that's polynomials. So we've kind of gone through weeks 4, 5, 6. So next is week 7, where we've got, well, you know what? Some of the things that you might be asked about are vertex of a parabola. So I can, oh, we can use k of x to find the vertex, because that's a quadratic. That will have a vertex. So let's say you were given an equation here and you needed to find the vertex. So the vertex is at x equals negative b over 2a. So b is the middle number, and then a is the first number, which in this case is just a 1. So we don't have a coefficient there. And we want to be careful because it's negative b, and b is already negative. So that's actually going to end up with a positive there. And then we have 2 times 1. So that would give us 2 over 2, which is equal to 1. But when we give the vertex, we want an ordered pair because it also has a y value with it too. So you also need to plug in that value into your equation, into your polynomial, so you can find out what the y value is at that point. So if x is 1, I'm going to plug that in. So I have 1 squared minus 2 times 1 minus 15. So 1 squared is 1, 2 times 1 is 2, so that's minus 2 minus 15. That gives us negative 16. So that's essentially the y value at the vertex. So your vertex would be the ordered pair 1, negative 16. Let's see, if you're asked to find the x-intercepts of something, you just set it equal to 0 and solve. So pretty much all the zeros, those are x-intercepts. So those are kind of interchangeable. You can also, I recommend anything that says to graph, I would use Desmos to put in the graph. Just make sure you're in the same scale, because most people get things wrong because their scale is not right. Let's see, we've got graphing. Let's do some transformations. And since we haven't really covered anything with week 7 stuff, let's do a transformation with week 7. So let's see, alphabetical order, H, I, J, K, L. I don't want to use L. We'll use a function called M. So let's say you have a function M of x, and it is e to the x minus 2. And you're asked about transformations. So this, if we ignore the minus 2, you're looking at a function that's just e to the x, which is an exponential function. And when we have transformations, anything that happens to the x is a left or right shift. And it's always the opposite. So we have this minus 2 that we subtracted from x. So we're actually adding 2 to the x values, which means we're shifting it over to the right. So that is a transformation where you shift right 2 units. So anything that happens with the x is the opposite sign. Now, if I had that same function, and let's say I have a minus 3, if you have something not with the x, separate from the x, that's a shift up or down. So I should point that, oops, one of my orange. So that minus 2 is a shift right 2 units. But if it's not with the x, it's separate from the x, that's a shift up and down, and that you don't change the sign. So minus 3 means we're shifting down by 3 units. So those are the kind of transformations you may see, and you could have functions with those same transformations that are not, say, e to the x. Let's say you had an absolute value function. So if you had an absolute value function with the same transformations, you have the absolute value of x, so that minus 2 happens inside with the x, and then the minus 3 would be after it. If you had, say, a quadratic, your transformation again happens with the x, so that would be x minus 2, that's where the square happens, and then the minus 3. So you can do something with the square root. That same transformation, we'd have x minus 2 inside the square root, the minus 3 outside. So you can kind of see a pattern. The same transformation happens, it's just the function is changing. So if you're asked about the transformation, you need to look at, okay, what is happening to the x? Is the x being changed at all? And then what is happening afterwards? Is there anything going up and down? If there's no number added or subtracted to x, then there is no left or right shift. If there's no number added or subtracted at the end, then there's no up or down. So not everything has both transformations, but that's sort of how transformations go. And then if you have a number in front, that's just a stretch by that number. So if it's like if there was a 2, then that would be a stretch of 2. We're multiplying everything by 2. And if we had that same stretch, it would just be in front of all of these different functions. And if there was a reflection, it would be a negative in front. So a negative in front of that function would reflect it upside down. So if I had like a negative, let's say 2, I'll use the exponent again. Let's use natural log just because we can. So if I made a new function r of x equals, so if we had like negative natural log of x minus 2 minus 3, that negative in front is a reflection. And then we are still shifting 2 to the right and down 3. Do you guys have any questions on transformations?
I do not.
Okay. Let's do a variation problem, because I know a lot of people get kind of stuck with that. Because last week I already did some like condensing logarithms and expanding. I'm not going to go over that, but let's do a variation. So let's say you're told that y is directly proportional to the square of x. And you are given, let's say x equals 2, y equals, I'm just making these up, so these numbers could be gross. Find the model. So if you're given something like that, we need to do transformation. So the word is always an equal sign. So we have y equals. Direct proportion means you're multiplying k times something. And then we have the square of x, which is x squared. So this translates to y equals kx squared. When you're finding the model, you need the equation with a number for k. So we need to find k by plugging in what we have for x and y. Yeah, this is going to be, I'm going to flip-flop x and y here. That's going to come out a little nicer. So let's make x 5, y 10. No, that's still going to be, let's make y 100. There we go. So you're going to plug in your numbers for y and x. So y is 100, x is 5. So that's going to be 5 squared. And you're going to solve for k. So 100, 5 squared is 25, so equals 25k. Then we're going to divide by 25 on both sides. So 100 divided by 25 is 4. So 4 is equal to k. So when it says to find the model, your final answer is that equation with your value for k plugged in. So the model then would be y equals 4x squared. If you were given a problem where instead it said directly proportional, it said inversely proportional, that means it's k divided by whatever follows. You could have a direct proportion and an inverse proportion, and you just have to write those in order. And if you have joint, those are multiplication, and there may be like more than one variable there. Any questions?
No.
Okay, let's do a problem where we are solving an exponential. So let's say 2 to the x minus 5, and this is, I'm making this up, so this could be, I don't know how this is going to come out. I'm just completely making this one up. So let's say you're told you want to solve for x here. So when you have x in the exponent, you have to get it out of the exponent by taking a log or a natural log. And you could do a log base 2, but we don't have that on our calculators. So you can do a log or a natural log. Most calculators, well, it depends on what calculator you have. My calculator has both log and natural log. If you have a graphing calculator, it generally only has natural log. So I usually do natural log as my natural choice because my graphing calculator only has natural log. So if we were to do natural log, you would have to take the natural log of both sides to get that x out of the exponent. So I'd have the natural log of 2 to the x minus 5 equaling the natural log of 40. And by doing that natural log, then you're allowed to take that x minus 5 that's in the exponent and put it in front. Now because x minus 5, that whole thing is together, that whole thing is multiplied by the natural log of 2. So you need to have parentheses there because you are basically multiplying those. So you would be, you'd want to distribute, and it's going to get kind of gross. You could choose to put that in your calculator and get decimals. I generally wait till the very end, just so that I don't have too many rounding errors. So a nice thing about not multiplying through is that I can divide both sides by this natural log of 2. And so that would cancel that out, and I'm just left with x minus 5. And then I have this natural log of 40 over the natural log of 2 thing. Then if you're solving for x, then you just have to add 5 to both sides. And so then x equals the natural log of 40 over the natural log of 2. Then I have this plus 5. And now this is where I usually put it in my calculator, because that way I'm not rounding until the very end. So I do the natural log of 40 on my calculator. That's 3.689 if I do 3 decimal places. And then the natural log of 2, so that's 0.693 with 3 decimal places. So then I want to divide 3.689 divided by 0.693. 5.323 plus 5. So then your answer would be 10.323. And if you use the log instead of the natural log, you would have the log of 40 divided by the log of 2, and you'd still be adding 5. You get the same exact answer. You might be slightly different just due to rounding, but you should get the same answer. It should at least match in the first 2 decimal places, depending on how far you round it out. So when you're solving something with an exponent, it really doesn't matter. I use whichever's easiest on my calculator there. Do you guys have any questions about that?
No, not really. Just listening.
Okay. And then I think the last thing that is going to be on the final is just like a system of equations, which is what you covered this week, so I can do one of those. So let's say, and this could come out really gross because systems are really hard to come up with nice answers to, which is really unfortunate. And let's say negative 3x plus 6y equals 12. So I don't know. These could come out really gross. I really have no idea how this is going to solve. You're given a system, so you have these 2 equations, and then your choices are to solve by substitution or elimination. I think for most people, substitution is the easiest when you're starting out. And solving by substitution means that you are going to solve one of the equations for x or y, and then plug it into the other equation. And it doesn't matter which one you pick. I'm just, in my head, I'm kind of playing around which one seems to be the easiest. And the second equation will actually be a little bit easier if we solve for x, because I'd be dividing everything by that negative 3 in front of the x, and it's going to come out nice without any fractions. If I solve for y, I'd have to divide by 6, so I get some fractions. And in the first equation, I'd either have to divide by 2 or divide by negative 5, and those would come up with fractions. So I just kind of look at it and look at the coefficients. So I'm going to solve this for x. So that means first I need to subtract 6y from both sides. So I get negative 3x equals 12 minus 6y. Then I'm going to divide everything by negative 3. So that I get x equals, then 12 divided by negative 3 is going to be a negative 4, and a negative 6 divided by negative 3 is going to be a plus 2. So that's going to be plus 2y. So since I solved the second equation, I'm going to plug this into the first equation. If I plug it back into the second one, it's not going to get me anywhere. So the second equation, or the first equation, I have 2 times x, so that's going to be negative 4 plus 2y minus 5y equals 10. And I need to put the parentheses there to make sure that I'm multiplying everything by that 2. So I'm going to distribute 2 times negative 4 is negative 8. And then 2 times 2y is going to get me a 4y. Oh man, I think I got really lucky. This is going to come out nicely. Wow. I got really lucky creating these numbers. Usually it doesn't work out. So I'm going to add my like terms. 4y minus 5y. 4 minus 5 is negative 1, so that's going to be negative 1y equals 10. Now I have that negative 8, and I want to solve for y, so I'm going to add 8 to both sides. That gives me negative 1y equals 18. So you don't want to forget that negative that's in front of the y. So we need to divide both sides by negative 1, and this gives us a negative 18. It's a big number, but it actually is a whole number. So now I need to replace that into my expression or my equation with x so I can find out what x is. So x is equal to negative 4 plus 2 times y, which is negative 18. So that's negative 4 minus 36, which will give us negative 40. And now when we write our answers, we always write them as an ordered pair, so that's going to be negative 40, negative 18, because it's always x first and then the y. So that is solving by substitution. You pick an equation to solve for a variable, then plug it into the other equation, solve, and then put your answer back into like the first equation. And then that will get you your answer there. And if at any point you come up with a contradiction, that means there's no solution. And if you end up with, if your variables disappear and all you have is like 0 equals 0, then there's infinite solutions.